Okay, this lesson is for section 4.4, modeling with functions. We're going to take real-world scenarios and then try to come up with functions that will accurately model that scenario. So this is typically a pretty difficult section for students, and this is a really important section also because it lays the foundation for you for next year when you get into calculus and Calc 2 and Calc 3 when you start taking those kind of courses in college. You're going to do a lot of modeling situations and real-world application problems. So this is going to give you hopefully a good foundation for doing those type of problems. So I've got some suggested steps here. One, make sure you're always picturing the problem, like drawing out a picture, defining your variables, and then labeling your picture according to those variables. You want to make sure you're accurately visualizing these problems because they are so abstract. And then finally, after that, then you can come up with your equation. Okay. Another thing is make sure you look at your front cover of your textbook for some geometry review. This is really important. We're going to assume that you know certain things like the area of a circle, that kind of thing, but just go ahead and review that. Again, it's in the inside cover of your textbook. Now the notation with your functions here are going to be given in function form, and I've got this little formula here. You're going to express f in terms of x. So when I express f in terms of x, this is the notation that it ends up looking like. If I were to express area in terms of width for function notation, that is a of w now, the area in terms of the width. So I've got all these examples here written out for you so you can kind of see, you know, what you should end up seeing as far as your function notation to the right. I want to preface this that these are just example problems and no two problems are going to be exactly alike, but you do want to make sure that you can understand the similarities between problems, and then from there you can problem solve each one. So let's start. I've done a lot of intro here. Let's actually get going on a problem. Alright, problem number 1 says the perimeter of a rectangle is 50 feet. We are supposed to express its area as the function of one of its side lengths. So right away I want to notice that it's saying area is supposed to be a function of the length of a side. So going back to my function notation, I'm supposed to express area in terms of side length. So let's do area in terms of length. So that means I'm doing A of L here. That's what I'm trying to find. Okay. Now the area of a rectangle is just length times width. What this means is if I want to express it in terms of length, I don't want to see any other variable here that's not a length. So I don't want this W, basically, is what I'm trying to do, is make sure that I have only lengths appearing on the right-hand side of this formula. So I'm going to go back to the original statement here that says the perimeter of a rectangle is 50 feet, and I'm going to show that out here in a picture. So I have length and width, and even though I don't know the length or the width, I do know that if I were to express perimeter, it would look like this. I also have this constraint here. Constraint on this problem is that the perimeter is equal to 50. So now I have an extra step here. I can plug in 50 for this perimeter. Okay, now I have an equation, not just an expression, but an equation that relates length and width with an actual number here. And again, I want to eventually get my area function in terms of only length. I want to get rid of the width. So what I do now, and this is maybe counterintuitive for you, the variable that you're trying to get rid of, this W, is the variable that you're going to solve for over here, so that eventually you're going to use the technique of substituting that into over here in this equation. So let's solve for W here so you can see what I mean. I'm going to subtract that 2L, divide out the 2 now, and I get W equals 25 minus L. So this now is W in terms of L. I can now substitute that back into my original function here with area as an expression of length, and now I have area area with reference to length is now length times 25 minus L, because again this represents just W. So now I have my area as a function of length, and if I want to simplify that, I have 25L minus L squared. So this is now area as a function of length. And that's the end of the problem. It doesn't ask me to do anything else except for to express the area as a function of the length of a side. Okay, problem number 2 says a rectangle is inscribed in a circle with a radius of 5. Express the perimeter as a function of the length. So this time I'm trying to express perimeter as a function of length. So P of L is what I'm looking for. Now the perimeter of a rectangle is just 2L plus 2W, right? We just talked about that before. And again, I don't want to see anything that's not an L on the other side. I need all my variables to be in terms of the L. So now I know now which variable I want to get rid of. Okay, so let's go back to this first part of the problem that gives us our constraint here. So our rectangle is inscribed in a circle. So we have a rectangle that looks like this. The radius of this circle is 5. So in other words, the diameter is 10. Okay. Now, the length and the width of this, actually it doesn't really matter, I guess, which one I label as L and W, but let's just keep it consistent. Let's put length here and width here. So the length and the width here of this rectangle would normally, just be given by, if we were trying to express this as, I guess, perimeter 2L plus 2W, but that doesn't get us anywhere here. What I need to do now is look and see what I can relate in my picture, some type of rule that assigns L and W some sort of length. So when I look at this, I say, oh, this is a right triangle on the inside of this. And I know that any right triangle, Pythagorean theorem always works. So if I add L squared plus W squared, I should expect to get 10 squared, 100. Now I have an equation that actually relates my two variables, and now I can solve for one in terms of the other. So again, I want to get rid of the W here, which means that I need to solve for the W here. So now I work on isolating the W, so I subtract that L squared over the other side. And now I take the square root of W. I don't want to include the negative here because we can't have a negative side length for our width. So we're only going to take the positive, and we have square root of negative L squared plus 100. Now I can take this and substitute that in for W in my function, P of L. So the perimeter in terms of length is 2 times the length plus 2 times the square root of negative L squared plus 100. And this is my function written in terms of the length. Okay, now in problem number 3, it says let P, just any point, x, y, be on the graph of x squared minus 4x plus 9. We are supposed to express the distance from that point to the point 6, 0, and relate that as a function of only one variable. So in other words, distance is going to be used, either d of y or d of x. It really doesn't matter which variable you choose, but you're supposed to relate the distance in terms of only one variable, because normally distance formula is given by finding the difference between your x coordinates, squaring that, and the sum of the distance between your y coordinates as well. So what we want to see, if it's in terms of x, let me erase this, if it's in terms of x, I don't want to see any y's, okay? Now, let's just draw out a picture to kind of help us to understand what we need to do here. Alright, so I'm going to graph this function and pick a point on it, and then draw the distance between that point and 6, 0. Alright, so when I graph this, I know it's a parabola, I know that it opens up. The only thing is I don't know if it should open up like this, and it really doesn't make a difference, I guess, but I don't know if it opens up like this or here. If I want to get it a little bit accurate, I'm going to check the discriminant, b squared minus 4ac, to see how many solutions it has, if it has real solutions or not. If it has 2 reals, then it looks like this. If it has 1 real, it looks like that, where it touches. And if it has no reals, then it looks like this. So when I check this, I get 16 minus 4 times 1 times 9. I get a negative value here. So that means it has no real solutions, which means it's something like that. Okay, so here's our quadratic. I don't really care where it's at, but just for the sake of being a little bit more accurate, I check to see where it's at. Now, I'm going to place a point somewhere on this parabola. Let's call that P, and the coordinates here are x, comma, y. Okay. Now, the point 6, 0 is about right here. Okay. let's find the distance between those 2 points first. Okay, so the distance between those 2 points is going to be given by the square root of x minus 6 squared plus the y-coordinate here minus 0 squared. Alright, now this is actually really close to what we want it to be, right? We're supposed to express distance in terms of only one variable. And if I want to do that in terms of x, then that means I need to get rid of this y. Okay, here's where the very abstract part of this has to come into play. When you look at the coordinate that you already wrote here for p x comma y, we actually know something about this y. We know that this y output is equal to x squared minus 4x plus 9. This is what the y equals, okay? So in other words, if I want to substitute that and find the difference between those two values, well then here, this is just x squared minus 4x plus 9. That would give me the y output if I were to plug it in and I get the y output here. So this is now, if I substitute that in here, this is now in terms of one variable. So d of x is equal to the square root of x minus 6 squared plus x squared minus 4x plus 9, and then the minus 0 here really doesn't matter, squared. And so this is my function of distance in terms of one variable, x. Okay, in problem number 4, it says a right triangle has a vertex on y equals 25 minus x squared, one at the origin and one at x0. Express the area of the triangle as a function of one variable. Okay, so I see that I'm supposed to write the area as a function of one variable, so that means I'm taking a of x or a of y, so I only have two variables here, x and y. And the area of any triangle is going to be given by 1/2 base times height. Obviously I can't use base or height, I need to have it in terms of just one variable. But this is ultimately what you're trying to fit your function into with the given constraint that one of the vertexes on 25 minus x squared, one's at the origin and one is here. So we're going to use all that information to try to eventually substitute values in for the base and the height. Alright, so let's draw in this picture. So I have a right triangle. Now, one of the vertices of that triangle is supposed to be at 0, 0. One is supposed to be at x, 0. Okay? Now, the third is on the parabola 25 minus x squared. Oh, the reason why I'm putting x, 0 on the right-hand side here is because I'm just going to make and assume x is positive. Okay? So, let's draw this parabola. Well, it's shifted up 25 units and then reflected over the x-axis also. So if I were to graph this, it's pretty terrible, but it has intercepts at 5 and -5. Not that that really typically matters, but this is the parabola. It's facing downward, and it's got a high point and its maximum at 25. Now, if I'm going to draw a right triangle in here, I need to make sure, let me just redraw this because it's so bad. I'm going to draw it so that I've got a height here, and that, oops, right here. Okay, so this point, excuse me, is where I'm going to place that parabola, or place the point on the parabola, and I'm going to call that point x, because that has the exact same x input. If it's supposed to be a right triangle, has that same x input, and then when I express the y coordinate of this parabola, well, if I plug in x into here, I get 25 minus x squared. Okay, this is the output that I would get by plugging in x into that parabola. So now I have at least everything in terms of x, so that's going to be helpful now when I express the area over here. So let's take a look and say, okay, well, the area of this triangle should be 1/2 times the base times the height. Okay? The base is going to be given by x minus 0. That's the distance between, this origin and the point x0, or just x. So I have the area in terms of x is equal to 1/2 times the base, which is x, times the height now. The height is going to be taking my y value, subtracting this y value, 0. So 25 minus x squared minus 0 is just 25 minus x squared. So the height here of the function of that triangle is 25 minus x squared. And now I have a new function in terms of x. And if I simplify that, I get 25 over 2x minus 1/2 x cubed. And this would be the area in terms of just one variable. Okay, problem 5 says a piece of wire x inches long is bent into a circle. We're going to express the area of that circle in terms of x. So area of the circle in terms of x. Now the area of a circle is pi r squared, which tells us that we need to get rid of the radius here. We need to be able to express the radius in terms of x. So let's work on the first part here, which is giving us the constraint. So we started with, a piece of wire that's x inches long, and then we bend that so that it forms a circle. Well, right here, that's telling us a constraint. We know that the circumference of this circle has to equal x units long. So circumference, let's start with circumference. Circumference is 2 pi r, and since the circumference is equal to x, now I have an equation that relates r and x. So again, I want to get rid of r over here, which means I need to solve for r here. So I have r equals x over 2 pi. And now I can substitute this in for r so that I get it in terms of one variable. So a of x is equal to pi times my radius, which is x over 2 pi, squared. And if I simplify this, I end up with x squared over 4 pi. Okay? So a of x is equal to x squared over 4 pi. And there's my function in terms of x. Okay, number 6 is an example of a problem that we might actually give you the surface area or volume formulas for, but hopefully you remember a little bit from geometry. I know it was a couple years ago, but you can also look inside your front cover, because I don't think in the book that they give you every single one of these. Like in the problem, you'll have to look it up in the front cover of the book. Anyways, it says a right circular cylinder has a volume of 10 cubic centimeters. Find the surface area, S, as a function of the radius of the base. So we want to find the surface area as a function of the radius. First, let's talk about surface area. So surface area of a cylinder, if you split up this cylinder, it's made of 3 different parts. You got 2 circles plus this part, that I guess forms wrapping around these circles. It's actually a rectangle. The dimensions of that rectangle are the circumference, because if you unwrap it, this piece going around represents this distance here, and that's just the circumference of the circle. And then this is, of course, just the normal height of your cylinder. Okay, so therefore the surface area would be, since we have 2 circles, 2 times pi r squared plus 2 pi r times height. That gives us the area of this rectangle. Alright, now I only want to have my surface area in terms of the radius. I need to get rid of this variable h. So let's go back to the original sentence that gives us a constraint. It says a right circular cylinder has a volume of 10 cubic centimeters. When you do volume of a prism or a cylinder, you're always finding the area of the base and multiplying it by the height. That's how you find volume. So the volume of this right circular cylinder is going to be found by taking the area of your base, pi r squared, multiplying that by the height of the overall shape. So pi r squared times height gives us the full volume. Well, the volume is equal to 10 cubic centimeters, so I already can substitute that 10 in here, and now I have 10 equals pi r squared h. Now I can solve for h so that I can eventually substitute that value in. If I solve for h, I end up with 10 over pi r squared equals the height. So now I take this and I plug it in over here, and I end up with S of r equaling 2 pi r squared plus 2 pi r times 10 over pi r squared. Simplifying, I end up with S of r equals 2 pi r squared plus 20, and then the pi's are going to cancel, one of these r's is going to cancel, 20 over r. And there is the surface area of the cylinder in terms of the radius of its base. Okay, in problem 7 it says two numbers summed to be 100. We're going to express the product, p, in terms of a single number. So the product, p, is usually just found by taking two numbers and, multiplying them together. But now I want to make this a function, so I'm trying to make it into a single number. A function of a single number. So I'm going to say p of x equals x times, instead of y, I need to get rid of y. Okay? So I'm letting x and y be the two numbers, by the way. I haven't really defined any variables, sorry about that. So let's say let x equal one number and y equal the other number. Alright, so x plus y, my constraint is that x plus y must equal 100. That's their sum. So I know that I've already got the perimeter or the product written over here, and I don't want to see a y there, which means I need to solve for the y here. So by subtracting the x, I end up with negative x plus 100. I'm going to take that and substitute that into here to get x times negative x plus 100. And simplifying, I have the product in terms of x equaling negative x squared plus 100x. And this is my answer in terms of a single number. Okay, last problem. Last problem here says the revenue is equal to the price per unit times the number of units sold. And hopefully that makes sense to you, that the most money that they're going to accumulate is by charging a certain price and then selling however many they sell. That's the total revenue of something. Now the price is a function of the number of units produced. Okay, this is a demand curve. This is something that we talked about in the first section when we looked at like marginal costs and that kind of thing. But the price is equal to the marginal cost times x plus your initial cost. Now they give us the demand curve and they say it's p equals negative 0.5x plus 6. We're supposed to express the revenue as a function of x. So let's start with the revenue they give us. It says revenue equals p times x, where p is your price, right? Well, I want to express revenue in terms of only x. I want to take r of x. So that means I need to get rid of this p and only have it in terms of x. So then I look at the constraint. They gave me the constraint. They said it was price is equal to negative 0.5x plus 6. So in this case, I already have the p solved for. This problem is actually really, really easy. I've already got the p solved for, so I substitute that value right into here. And I have r of x equals negative 0.5x plus 6 times x. If I simplify that, I get negative 0.5x squared plus 6x. So this is r of x. It's the revenue in terms of a single variable. It's a function now of x. Okay, that's the end of the lesson. Hopefully you got some good, problems to form a basis for how you approach the rest of the problems in your notes and on your future quizzes and tests.